Okay, good evening, everyone. Welcome to the ICorr Aberdeen branch AGM technical evening. We'll still give a few more minutes just to allow some more participants to join us tonight before we start this evening's proceedings. So in the interim, I will be on mute for a few minutes and we will start at about 18:05. Thank you, everyone. Just a minute, we'll be right back. Right, once again, good evening, everyone, and thank you for making it this lovely, balmy evening. Tonight we're going to have our annual general meeting, and that will be followed by a technical presentation by Peter Beck and Simon Fenton of IRISNDT. So we'll just make the start. Right, so our 2024 branch executive committee really put in tremendous work to make the 2023-2024 technical program a success that has been so far. Our committee members are as indicated on the slide. We had a new member join us during the 2023-2024 technical session, and that was Mrs. Stephanie Okoye, a seasoned corrosion engineer, currently working as a corrosion engineering consultant with VISIS. In the position of chair was my humble self. Our vice chair was Billing Chair. Our internal and external branch secretaries were Liang Ling Bei and Dr. Nigel Owen. Our financial officer was Dr. Ben Roberts. Our sponsor officer is Dr. Olubayo Latinwo. Our event coordinator also joined us this year formally, and that is our dear friend Ailey McDonald. Our university liaison and CPD officer was Leela Ramachandran. Our website officer, who is our national vice president, Dr. Yan Ngao. Our case study officer, Dr. Steve Patterson, who was in the hot seat for the 2022-2023 session when we had our YEP program hosted by the Aberdeen branch. And our national president is on our board executive committee as an observer. And that's the makeup of our committee. We would like to say a big thank you to our branch and sustaining sponsors, because without their help, this year would have been, the events that we hosted this year would have been really difficult. So a big thank you to them all, especially to Risco International and Risco Corrosion UK Limited for hosting the 2023-2024 Corrosion Awareness Day. So far, we have had 252 members elect to join the branch. We continue to welcome new members to the Aberdeen branch as it continues to remain vibrant. And sorry about that. As it continues to remain vibrant, and we do hope that you will choose the Aberdeen branch to make it your home branch if you choose to join the Institute of Corrosion. Our financial position for the Aberdeen branch continues to remain strong. We, at the moment, have 17 branch sponsors, about 16 national sustaining sponsors, and we did receive some revenue through our Corrosion Awareness Day event, which was held in August of 2023. The figures on the presentation just now are rough estimates, and these will be refined once we receive the final positions from our headquarters. We continue to seek new branch sponsors, so if you know of anybody that is willing to sponsor our branch, please direct the person to the website as indicated on the presentation. The cost is just £300 per annum, and the benefits are too many for me to go into right now. So I'll direct you to our website for more information. In terms of our event attendance for the 2023 2024 session. It continues to be quite strong and favorable and reflects a growing trend as we try to creep back to where we were pre-COVID. The branch this year made a decision to have our events as either solely online or solely in person. And that has yielded some benefits, although there have been some drawbacks as well. We'll continue to explore options and see which will be the best balance for both our branch resources and also for our attendance, both within the Aberdeen area and international. Our events that we've hosted this year are stored, archived on the ICorr website, as indicated on the slide in front of us. If you go to www.icorr.org, the Aberdeen sections site, within the webpage, you'll see our 2024 presentations and an archive of our presentations dating back over 10 years. A lot of good technical content is stored there. We also have a YouTube channel as well, which has live recordings captured during our technical presentations. Our news page is also archived on our branch page, and we also have a LinkedIn page, which you can like and follow on LinkedIn. Our program for the 2023-2024 session started in August last year with our Corrosion Awareness Day, which was hosted, as I've said earlier, by Risk of Corrosion UK Limited. And that was an all-day event held at their premises in Bridge of Dawn in Aberdeen. In September, we had an event, a presentation by Alicia Keogh of the University of Manchester. And in October, we were graced with two events. One was an exhibition, which we held at the TECA, the Floating Offshore Wind Expo, where we exhibited the capabilities and benefits of the trainings provided by the Institute of Corrosion. And then later that month, we did have a presentation by Dr. Heike Hoffman of Intertech on routine monitoring to combat microbial issues in oil field process systems. Later that year, I think the last event for 2023 was a presentation by Dr. Douglas Mills and Tianyang Lan on electrochemical noise as a means of monitoring or assessing organic coatings. In January, we had a presentation by Dr. Steve Patterson, one of our very own, on applying materials experience from oil and gas production to carbon capture and storage in the Northeast. In February, we had a presentation by Mark Smithson of Subsea 7 on predictable pipeline performance with polymer liners. And in March, we had a technical event by Dr. Chukuma Unoha of Cantrix Corrosion in Canada on advances in comprehensive integrity assessment of buried pipelines used non-contact magnetic gradient tomography. Unfortunately, we were not able to have our joint event with the Marine Corrosion Forum in April last year. So we had just the industrial visit to the MCIMB premises in Dice in Aberdeen. And in May, unfortunately, we also could not host our weekly webinar series. So we just had our joint event with the ANPP on the proportional hazard assessments for different pipeline coating types by Susan Jacobs of One Gas, Tulsa, Oklahoma, in the United States. Our presentation today will be by Peter Beck and Simon Fenton of IRISNDT on a metallographic replication of in-service plant, and our flagship event is due later this year on the 27th of August. It is going to be our annual corrosion forum, and the theme is corrosion management in the energy sector. It promises to be a well-attended and exciting event. The registration deadline is the 17th of August. I would implore everyone in attendance tonight to sign up for the event if you're local. And if you could travel down, we'd appreciate your presence as well. And this is the snippet from the flyer. It's going to be an all-day event on the 27th of August at the EngTech premises in Altons in Aberdeen. And our costs, we've decided to keep the same as last year at £90 per delegate. However, if you are a corporate sponsor, you can then have 2 delegates from your company attend for free. So for the 2024-2025 technical year, we are proposing Mei-Ling Chair as the chair of the branch, Aberdeen branch, and vice chair in the person of Ailey McDonald. So a virtual round of applause for our incumbent chair and vice chair. They have worked hard this year, and I feel confident that they will continue to make the Aberdeen branch a branch to stand out in the years to come. And this is proposed by myself and seconded by Steve Tate. So our branch executive committee continues to evolve, and we currently have 3 vacancies. So if you know of any interested people who might be willing to serve on the executive committee, please, by all means, contact the branch through the branch email, and we will definitely give you a shout. Currently, we have 1 new person joining our branch in the person of Mr. Johnny Morton, and I'm very confident that he will fill in one of these slots to the best of his abilities. So these are just some photographs from some of the events that we hosted in the 2023-2024 technical year. And as you can see, we delve both into the social, as you can see for the dinner photographs, and the technical presentations were well attended, as you can see as well. We do look forward to hosting you guys in the 2024-2025 program that's going to start from August of this year. And please, by all means, attend both in person and virtual if you can. Sign up with the Institute. We'd appreciate you being there. Now, without much ado, I will start our introductions for our presenters for tonight's technical session. They are in the person of Peter Beck and Simon Fenton of IRISNDT. Peter is a senior metallurgist with over 8 years experience split across the power and automotive sectors. His background includes corrosion characterization in power boilers, materials testing within a UCAS accredited laboratory, and failure analysis of various metallic components from a wide range of industries and manufactured from various metallic alloys. He has significant experience in examining metallurgical replicas from in-service plants, assessing them for mechanical and corrosion-related damage mechanisms. Simon Fenton has over 30 years experience in the power industry, where he held several senior technical roles. His key skills are component inspection and integrity assessment, failure analysis, and legislative compliance. He is currently the technical manager of asset integrity engineering based at the IRISNDT's offices in Derby. So please give a virtual round of applause while we welcome Simon and Peter to deliver their presentation. Over to you. I will stop. You can start sharing.
Okay, thank you very much, Siji, for the introductions. I'll just share my presentation. Okay, thank you very much to the Institute of Corrosion Aberdeen branch for inviting us. So we're going to give a presentation on the metallographic replication of in-service plant components. So as I say, it's by myself, Peter Beck, and Simon Fenton. We're based at the Derby branch of IRISNDT. So this evening we're going to give you a bit of an introduction to ourselves and to IRISNDT. Obviously, Siji's given us the introduction to us. We're going to go through what a metallographic replica is, how they're produced, the uses of them, and then how they are assessed. So what we can see in terms of microstructures in the metals, and then specific damage mechanisms. And Simon's going to give a couple of case studies of things that we've looked at recently. So just a little background about IRISNDT. So it's a Canadian company, originally started in the 1950s. It's grown through acquisitions, targeted acquisitions, I think it's fair to say, and also natural growth. So we've now got operations in the UK, USA, Canada, and Australia. We've got about 6 sites in the UK. Globally, we employ about 2,000 people. And I think there's about 41 locations worldwide. So the UK is probably about the third largest area for IRIS. So slightly confusingly, given the title of the company, we don't just do non-destructive testing, we also do destructive testing. So we do that typically in our lab in Derby. Our offering of services ranges from traditional NDT, so ultrasonic testing and MPI, those kind of things. We also do advanced testing, so like phased array and RVI, remote visual inspections. We also offer metallurgy on site. So that's typically the replication that we're going to talk about, in situ hardness testing and positive material identification, sort of chemical analysis. The three of those tests generally go hand in hand. So although we're talking about replication, quite often we would do those three sort of tests together. We also do metallurgy in our lab, and we also have a mechanical test suite, so we can do everything from tensile testing, hardness testing, and all of that supports our failure analysis that we do. We cover a wide range of industries. I think possibly noticed that both Simon and myself have got a main focus on power sector, but we do typically also cover petrochemicals, manufacturing, mining, many other industries, particularly with replication and failure analysis. It covers pretty much anything really. So we do cover other things. So let's get to what a replica actually is. So essentially it's a fingerprint of the metal surface. And so by that, I mean, you are essentially taking what's on the metal surface and replicating that onto another medium. Typically, there's two forms of replica that we use. One is an acetate sheet, which is what you can see there in the bottom image, which is put onto the metal surface. And then we take that off and put it on a slide. I'll explain that in more detail in a minute. And then there's another method, which is to use a putty type of material. So basically it's a two-part PU rubber type material that mixes down a nozzle. Again, I'll go through that in more detail in a second. Both techniques have advantages and disadvantages. One thing that they both can do is they can get down to about a micron in terms of resolution. So when I say a fingerprint, we're talking about an etched metal surface generally. And we would be looking at everything down to sort of carbides and phases and things like that. So I'm going to go to the next slide now, which is talking about the PU type of replicas. So as you can see from this, basically on the left image, you have a small applicator. So it's similar possibly to sort of a silicon tube, silicone like you might use in your bathroom. It's a two-part system though. So as you press the plunger, both parts are pushed through the nozzle. They mix in the nozzle. So you have an activator, a hardener. And then as it goes onto the surface, it will take up the morphology of the surface and gradually cure. Now you can get different cure rates, so anything from maybe 5 minutes to about an hour. So you may think, well, you want a quick cure time, but not necessarily, because once you've started the process, anything in that nozzle will start to try and cure. So if you've got a few components that you want to replicate, you would typically want something that actually cured over quite a long time, so that you had a long time to do your work. You'd get quite a few replicas out of one tube. With this type of replication is particularly good for any 3D type of objects, as you can see with this, looking at this sort of cog. So if you had a crack at the base of one of those roots, you'd be able to then essentially take the inverse image of that crack, and you'd be able to assess that and then have that you could store that indefinitely really. The disadvantages are that it's not flat. So I mean, that's quite obvious, but for some things, for typically the way we assess things is by optical microscope. So we would generally look for a flat surface. So this isn't what we typically use. But if you did need to use this, it can be for sort of corrosion pits, things like that, casting defects, those kind of imperfections that are sort of volumetric and three-dimensional. So that's one method of replication. And then the one that we typically use is this one with the acetate sheet. So the way that we would generally do this is we would prepare the metal surface, polish it to 1 micron finish, and etch the surface. Obviously, that would depend on what type of steel, stainless steel, aluminium, you know, any metal we can etch really. But so the etchants will depend on the metal itself. But then we would apply this acetate sheet. So basically, you would sort of gradually lay this sheet onto the metal whilst also applying acetone. The acetone has the effect of almost melting the acetate sheet, and this allows it to form the surface of the metal, if you like. So at this point, the acetate sheet will then gradually harden as the acetone dries off. You can see on this pipe that we've sprayed it black, and that the replica is also black. So the reason for spraying it black is to give us a contrast when we look at it under the optical microscope. One thing to say is that we typically do replication for creep assessments. So typically with that, we would look to replicate both toes of a weld. You can see in this image, we've replicated 3 positions. So 1 on one toe and then 2 positions on the other. That's because we've got a crack there that we actually replicated the crack tips. But essentially we want to capture both the weld metal and the parent metal each side of the weld. So we typically would have about 1/3 weld metal and 2/3 parent material in a replica, and that's why we need to take 2 generally, because the welds are just too large to get into one replica. And then the main advantage really with this method for us is that once you peel the replica off, once the paint's dry and everything, you can adhere this to a glass slide and flatten it with the back of another slide. Sorry, my computer's giving me messages. Once this is flattened, obviously that allows you to then put it under an optical microscope. So we're taking something that is a curved surface or an undulating surface and basically making it flat for assessment. So that's the real key reason we would use this method. The PU method would also give us the same resolution, but not the flat surface. So it would be very difficult to focus and assess a replica from that method. So this is the kind of thing that we can see from a replica. So we would typically look at replicas using magnifications between about 50 and 500 times magnification. The image you can see there at the bottom is taken at 500 times magnification. So you can see that really that's pretty similar to if we looked at an actual metal surface. We do get some imperfections from this technique. Mainly you can see this kind of white speckled appearance in some of the perlite regions, and that's an artifact of the technique itself. Obviously on different sites the cleanliness can be difficult to maintain, so they can sometimes get dust or scratches, things from lagging, things like that can all get stuck to the replica essentially. So it's important to try and maintain cleanliness whilst doing this, but generally we get something that's about as accessible as the metal surface would be. The key thing is this provides a physical record of that component at that particular moment in time. So if you then wanted to go back and compare it, you could go back in a few years' time at the next outage and compare the replica from the last outage if you needed. Sometimes assessments can be slightly subjective, so one person's idea might be different to another. So it's very useful in that sense to have that physical record that you can reassess if you need to. I suppose the key thing is to know when to use replication. There are times when it makes more sense to replicate than others. So we typically use this as part of an inspection monitoring system. So as part of an outage on a plant, doesn't have to be a power station, they would generally assess which welds might need replicating. Might not actually just be welds. Sometimes they also look at parent material. So some bends and other components can be subject to degradation. And then as plant gets older, you typically also look at the straight sections of pipe as well. But so you can either just look at it as a general inspection strategy. Also, sometimes we look at things that have uncovered by other NDT techniques. So the picture at the bottom is showing an MPI indication on a bend. So this was something that they were only going to do MPI on, and then obviously you can see the indication there. So that you can then you typically replicate the crack tips, and then you can start to understand a bit more about the degradation mechanism from that particular feature, that indication. We've also replicated on structural materials, structural steels after fire events. Obviously, fire can have a significant impact on the microstructure and degrade it and soften the material. So again, this is where I mentioned that we would also often do hardness testing. So we would do, for a fire, we might do replication and hardness testing to use as a double approach to assessment. Another thing that can be done is replicating any kind of welds or anything like that repairs or anything in plant or even before it's been in service. So quite often with stainless steels, we might be interested in sigma phase or something like that that's formed. So that's where that kind of QA process would come in. So I suppose it's important to compare replication to assessing a component directly. I suppose in an ideal world, you would always assess a component directly, but generally it's not practical. So sometimes the geometry of the component just isn't suitable for that. So you can see one of our replicators here polishing a bend. Once he's polished that and it's completely etched and everything, then in theory you could try and put a microscope onto that pipe and assess it. The problems are obviously it's curved, so in 2 dimensions there as well. So focusing would be very, very difficult. Also just holding the microscope into that position. And also there doesn't look a great deal of access there. So obviously the microscope has a certain length to it to look down. So it may be that just you wouldn't actually have enough space to actually see down the microscope at that point. The other consideration is we're often working when we're replicating off scaffolds and very small areas. So in order to just get there, to take a microscope quite often wouldn't even be practical, just in terms of logistics there as well. The other thing is that if you were to try and use portable equipment, quite often it's not as user-friendly as static equipment. So from a microscope point of view, the field of view is generally much smaller. It's much more difficult to just to operate and focus, as I say, on a curved pipe, it's not easy to focus, get a nice field of view. And again, that's the whole point of replicating, really, is to get that flat surface from what would otherwise be a curved surface. And we don't have any problems flattening out those kind of compound curves either. One thing is also it can be used on failed components. So I appreciate not in service anymore, but sometimes when we're doing a failure assessment, before we cut something up, we might replicate the original surface. So we've got a record of that, so that as we cut up, we can still compare what the actual surface was like as well. So there are some limitations to replication. Firstly, there are some features of the metal that aren't transferred into the replica. So these are typically things like the color of the etch. So sometimes if you're looking for sigma phase, for example, ideally you would use a colored etch so that it etches the sigma, a kind of a browny color. One thing is that with this, it's not got any color. It's always going to be black and white, basically. So that is a limitation. So you'd have to make some allowances. So sometimes it might be that you'd have to say it's consistent with, but it's not definite. The chemical composition obviously isn't transferred. It's an acetate replica. It's not the metal itself. And for that, we would use positive material identification. So you can see in the top image, we have an XRF gun. So it's X-rays are fired at the material. The incoming X-rays are assessed and identify the different elements in. Typically, this is for steels and stainless steels. Other materials can be done, but we typically stick to steels and stainless steels. And then lastly, the mechanical properties of the material. Again, obviously it's an acetate replica, so they're not transferred. So this is where we'd use portable hardness testing. So the bottom image there is of a UCI type hardness tester, which gives essentially like a Vickers hardness equivalent to about HV5. So from that, we can get most of the information from a material to support the replication technique. I suppose all portable equipment has considerable limitations compared to static equipment, and in an ideal world we'd do destructive testing, so we would do a proper tensile test and things like that. These techniques will always have much greater uncertainties. So you'd have to already have some idea of what the material is that you're testing. And then it's more about saying, yes, this is the correct material properties, and they match to the grade that you expect. So this is one of the uses we've had recently on replication. So we had these boiler tubes that had a heat tint on, so they're a stainless steel. Obviously this heat tint indicates they've probably been sort of up between 500-600 degrees. So the customer's concerned whether there was any degradation, whether they may be sensitized. So sensitization is carbides forming at grain boundaries, essentially. Potentially you could also get sigma phase forming at these temperatures, but it's probably on the low side for it. So this is one of the key things for replication, is fitness for continued service. And so we would typically look at things like, is it susceptible to corrosion? So has it degraded in a way that will make it susceptible to corrosion? Any kind of metallurgical degradation in the microstructure that might be mechanical or corrosion sensitive. So has it softened, things like that. Has there actually been any corrosion on the piece? So I mean, obviously this is an oxide, the heat tint, very thin, but sometimes we could potentially be looking at corrosion on a plant. We could also be looking at mechanical damage, so things like fatigue or creep damage would come into those categories. So in terms of what replication can offer an assessment engineer, the condition of materials can be affected by a lot of factors. So I'll start on the right-hand side of this diagram. These are the key things that we're looking for. So typically creep damage, which can be affected by a number of factors. So things like manufacturing defects. So in that, I include things like casting defects or original sort of tube bending or anything like that, as well as welding. Thermal inputs. So typically we're looking at power station components. So steam pipe work, things like that that are hot. Mechanical stresses, again, this would come from your pressure on the hoop stress on the steam pipe work, but also can be mechanical inputs from any out of alignment of pipe work. The system design itself can have an impact, and then also how long the plant's been in service for. Similar things really for fatigue, and then same for corrosion fatigue, and then I suppose corrosion would be affected by most of these really. So original defects, so any kind of casting defects might form voids and pits for sort of crevice corrosion, things like that. Thermal input, so if the component's hot, then obviously it's going to accelerate the corrosion. The process fluids, we come across a range of different fluids, various fluids used on power stations as well as the other plants that we look at. So yeah, acids, alkalis, the lot, yeah, it makes a big difference. The environment, obviously, so by that I mean sort of the general environment, atmosphere around the plant. Again, the system design, and then how long it's been in service for. So with replication, we can assess a lot of the features of these, and then they can help to trace back some of the any defects or anything like that in these list on the left. So in terms of assessment, I suppose the image on the left is typically the area that we're most interested in on a lot of the plant that we look at. So it's got weld metal there on the right, the heat affected zone in the middle, and then going into parent material. So we would typically assess an entire replica. So we would look at the weld and the parent material, as well as the HAZ there. And we would look at that at about 50 times magnification. And then we would focus on certain areas like the heat affected zone at maybe 500 times. We can go up to 1,000 if needs be. We would also, if when we look at the replica generally, if we see any sort of volumetric defects or anything, we would also obviously look at those in more detail. So on the image on the right, you can see the tip of a creep crack. So this is creep damage when it's quite severe, and it's surrounded by these creep cavities. So again, that's at 500 times magnification. That's that one. So you can see individual cavities. Simon will go through creep damage in a minute, I think. So I suppose I don't know how much everyone knows about metallurgy, so I'll just give a little bit of background on that. So typically we're starting off with something heated up into the austenite range. And then if we go through a slow cooling process, then if you're familiar with the carbon iron diagram, then you'll get something like the left-hand side. So you'll get a two-phase microstructure for a steel, comprising of the light-coloured grains, which are ferrite, and the dark-coloured grains, which typically would be pearlite. To be honest, in this image, they're probably more like bainite, which is somewhere between slow and rapid cooling. But still, you've got that quite distinct two-phase microstructure. The other option is rapid cooling, which stops the carbides from forming into these nice individual grains, and you get this sort of acicular structure, which we'd call martensite. So that's the effect of heat treatment on the microstructure of a metal. And then also the actual composition can have a significant effect as well. So taking two sort of extreme examples here, what one would be cast iron. So these top two images show on the left spheroid or graphite cast iron, and on the right a grey flake cast iron. So as I say, both of these would be termed cast iron. The real key difference is the alloying composition. And the key effects of that are that on the left you've got these nice nodules of graphite, sorry, and on the left they form these sort of flake-like graphite structures. There's various ways to document these. ASTM have a range of classifications. So they would classify the graphite into whether it's flake, spheroid, or graphite. They would classify the different sizes of graphite as well, and the grain size. The bottom images show stainless steels. Again, different only by their compositions, really. So on the left, we've got a super duplex stainless steel. You can see the light phase in that is austenite, and the darker phase will be ferrite. So it's a two-phase structure there. Whereas on the right, we've got an austenitic stainless steel. So it's a single phase austenite there. You can see that the grain boundaries, and you can also probably see some twin grain boundaries as well there. So these are the kind of microstructures that we can assess in replicas, and comment on the quality of the microstructure, any degradation, things like that. We can also look at casting defects as one example. So one issue may be that if you have a defect like this on the surface, then it could be indicative of porosity throughout the casting. That could give you leak sites through the wall thickness, or it could act as sites for corrosion to initiate. So this is an aluminium casting that we had. So from a dye penetrant inspection, we initially detected the pores. So they're quite difficult to see by the naked eye. So I've actually included an electron image of the actual. We were lucky with this that it was actually a failed part, so we were able to cut it up. So this is an electron image of the actual part. So you can see this pore, and you can actually just about make out the dendritic structure around where it's solidified. So it's basically a shrinkage porosity there. So the middle image then shows a microstructure of that at low magnification. So again, it gives us a chance to understand the porosity, the extent of the porosity, and then we've looked at the higher magnification image, which has given us an understanding of why this porosity might have existed. So these needle-like phases in the microstructure that you can see, they can tend to slow the metal flow as it solidifies, and that can cause these kind of shrinkage porosities. So all of that is something that we can cover with replication. So we replicate the surface, and we would be able to see these kind of defects and features. Another thing that we can do is looking for deleterious microstructures. Typically with stainless steels, one consideration is sensitization. So we can actually etch the structure very heavily and see if we get this kind of ditched structure, as they call it. So that's the image on the left, showing a sensitized austenitic stainless steel. In super duplex steels, we typically look for things like sigma phase. It can be an issue with austenitics, but more so with duplex steels. So we can replicate for that and look for that. And we can also look at the phase balance between the austenite and the ferrite in in super duplex steels as well. So that's what this image is on the right, sorry, is a super duplex stainless steel. So you would put a grid pattern across that and do a count basically to work out the percentage of austenite and ferrite, and that has quite a key impact on your corrosion resistance, the amount of austenite to give you that corrosion resistance. So in terms of corrosion specifically, we can use replicas to assess a number of mechanisms, potentially pitting corrosion. As I said, we probably use the putty type replica method for that. You'd then be able to physically measure things as well as do some optical microscopy. It would be limited due to the irregular surface, but we could do some. We'd also look at stress corrosion cracking. So that's this image on the left at the bottom. So that's showing the transgranular cracking that you typically get with stress corrosion cracking in austenitic stainless steels. We can also look at corrosion fatigue, similar again. So you typically look at the crack tips and look for oxides and things like that that would they would show up as a sort of a grey amorphous kind of region in the replicas. And then this bottom image is showing hydrogen cracking. So this is a putty type replica. So you can actually see that the intergranular cracking. So you've got the crystalline structure there of how the hydrogen has gone around the grains. So I think this is Simon's slides.
Right, thank you, Pete. Can you hear me okay?
Yeah.
Yeah. So yeah, as Pete said already, probably the most common application of the acetate replica in the power industry is to monitor for creep damage. And just to give you an indication of the scale of the replica exercises that we undertake, if we embark on an outage, a statutory outage for a gas-fired site in the UK that has pipe work in the creep range, we could be taking up to 1,000 replicas or more during a 3 to 4 week period. So it's quite labour intensive. We have a team of replicators to do that, and obviously people looking down the microscope. So it's a replication on an industrial scale, really. Now, just to remind you what creep is, it's a process of slow elongation of a steel. So this is a metal that's loaded below the yield stress, but over time, there's a time-dependent process that takes place to give you deformation. And this can occur when the operating temperature of a component is above about 30 to 40% of the melting point. Sorry, when it's at about 30 to 40% of the melting point, measured in Kelvin. So the damage itself forms on grain boundaries, and it's quite common in long-term creep to see voids and small cavities forming on the grain boundaries. But you can see this damage form as wedge-like grain boundary separation. This can occur when the stresses are very high and you get a short-term failure. And it can also occur at low temperature. We have something called low temperature creep crack growth. And that would tend to form wedges on the grain boundaries rather than cavities, the classic cavities. But all of this damage can be detected with the replica process. So there's a progression that you start off with cavities, and the next slide will illustrate this for you quite well. We start off with cavities, which then link to form micro cracks, and then the micro cracks form macro cracks. And this is the progression around the creep curve on the left there. So we've got strain plotted on the y-axis and time on the x-axis. And you can see that strain, we take an initial elastic elongation when we first load up the component. That's moving to point A. And then over a relatively quick period of time, we get what we call primary creep. So we get an acceleration up to point B. And then a lot of components will spend most of their life going from B to C in what we call secondary creep. So this is a steady state creep, sometimes called. And the creep damage is starting to form during that period. And then when the damage starts to accumulate and form those micro cracks, we move into the tertiary creep stage, and then on to final failure at point D. The creep process follows an Arrhenius relationship. So as a rule of thumb, for every 8 to 10 degrees C increase in temperature, you can double the creep rate, half the creep life. So controlling temperature on power plants is a very, very key thing. The other factors, as you're probably aware, are the stress that you apply, the alloying content, the heat treatment condition, and the grain size is also important. Next slide, please, Pete. So this is another view of that creep curve showing this progression of damage. So you've got in the bottom left there, you've got isolated cavities forming on the grain boundaries in this out of the secondary stage into the tertiary stage. Those cavities are then starting to align themselves on the boundaries, eventually forming micro cracks and then joining to form macro cracks. It's only at that macro cracking stage that we can use conventional NDT to find these cracks, this damage. Up to macro cracking, we need surface replication to find the damage. But we always use a range of things in our toolbox, really, when we're looking for creep. So it's surface replicas, but MPI and UT are very important for us. So MPI, magnetic partial inspection, allows us to cover the whole component. And we would typically carry out the MPI before we do the replicas. And this is so that we can target the replicas on any defects that are shown up by the MPI. UT, ultrasonic testing, is also really important because sometimes the creep damage can develop subsurface. So you're not always guaranteed to find the peak levels of creep damage at the surface. And this is true of things like butt welds and thick section components. So ultrasonic testing is also used as a key monitoring tool alongside replicas. Okay, next slide, please, Pete. So in terms of parent material, this shows, this is something we don't want to see, obviously. This is a 600 millimeter long creep crack in a main steam pipework bend on a UK coal-fired site. The site's now closed. So this was discovered in 2006. The plant had been in operation for about 200,000 hours, operating at 565 degrees C. So it's a low alloy steel, 0.5% chrome, half moly, quarter vanadium. The design life was 150,000 hours, so it's well past its design life. But at the time, we were monitoring 1 or 2 bends on that power station, each outage every 4 years with replicas and NDT. And the discovery of this in 2006 led to a massive escalation in the amount of replicas we were putting onto parent material. We were already looking at lots of butt welds, because they were known to suffer damage earlier in life. But the parent material, until this stage, had not really given us any problems. So there was suddenly an overnight need to train up new replicators. And again, it became replica on an industrial scale, really, to monitor this damage. And in this particular example, the creep crack that you can see on the outside actually started as global creep through the body of the component. The component was 65 millimeters thick. But in the latter stages, it grew very rapidly by a process of creep crack growth. So this is creep damage sweeping away at the crack tip and forming a very rapid progression of the creep crack. Okay, next slide, please. So this shows the typical replication pattern for a bend on a main steam pipe or a hot reheat pipe. So we have 5 replicas there. We've got positions 1, 3, and 5 along the centre line of the extrados of the bend. And we go either side of that with replicas 2 and 4, just offset from the extrados centre line. The NDT is also carried out in a band all the way along the extrados, but also all the way around the circumference of the bend at that midpoint, capturing the intrados of the bend as well as the extrados. And this was based on that previous slide I showed you, where not only did we suffer creep damage on the extrados, that was the worst damage, but we also found creep damage starting to develop at the intrados as well. So we, as a precaution, apply MPI and UT to all of those areas shaded in grey on that slide. Now this slide is applicable to a seamless bend. Now we do have in the UK examples of welds, bends that have been seam welded. There could be multiple seam welds, one on the intrados, one on the extrados, for example. And that gives us a requirement to throw more replicas at the inspection. So we could be looking at up to 15 to 20 replicas per bend. So it's a lot of effort to monitor for creep damage. Next slide, please. So moving on to welds now. This is a schematic of the convention that's used. It's a German convention to describe the development of cracks in different positions of the weld. So in the centre there, we've got the weld metal. On the far left and far right, we've got the parent material, the base metal. And then in between, we've got the heat affected zone. Pete talked about this earlier. But what I've done there is split that into the fine-grained heat affected zone on the outside and the coarse-grained heat affected zone on the inside, closer to the weld. Typically in the coarse-grained heat affected zone, we get things like reheat cracks you might have heard of. But my focus for this presentation is on this fine-grained heat affected zone, also known as the Type 4 region. And the Type 4 region is a particularly creep weak zone. If you show me the next slide, Pete, please. So there's 3 photographs there, starting on the left with a full view of a weld with a full through thickness Type 4 crack running through that weld. Photograph B shows this at high magnification, and you can see the creep damage forming in that Type 4 region, this fine-grained region. And then in the photograph there, marked C, you can see the individual cavities and areas where the cavities are joined to form both orientated damage and also micro cracks. So that's Type 4 damage, and that's a real problem for the industry. Not only is it called Type 4 damage, we also call that region the creep weak zone, the over-tempered region, the intercritical region, fine-grained region. So it's got lots of different names. But it's the same thing. It's a creep weak region of the weld. In that previous bend failure that I showed you, similar systems had suffered weld failures after 40,000 hours. And this was a combination of the creep weak zone, but also problems with things like the pipework supports leading to high system loads. So high system stresses acting on that Type 4 region. Next slide, please. And this is a recent example of a Type 4 crack that was discovered on a biomass plant burning wood. So this is part of the hot reheat steam pipe works, taking reheated steam from the boiler back down to the turbine. The branch there is the bypass part of the circuit. So if steam is dumped during a trip situation, it goes down that branch. Otherwise, it goes off to the turbine. And what we discovered there was a macro crack about 90 millimeters long in the pipe side, the main pipe side toe of that branch weld. And that's shown in more detail on the right-hand side photograph. So that's occurred after, again, about 40,000 hours of operation at about 540 degrees C. The material there is grade 91, P91. So this is a modified 9 chrome steel. And it's a particular steel that if you get the heat treatment wrong, you can suffer premature creep damage. So we're always quite wary of this material. Certainly use a lot of replication, a lot of NDT on circuits that are made up using that material. So what we needed to know in this case was what was the damage mechanism. Looking at that macro crack there, the possibilities are, could be a reheat crack, it could be a creep crack, or it could be a fatigue crack, any of those possibilities. So we used metallographic replicas to determine what we were looking at. and it was a creep crack. But we only found the creep damage at that one position on the flank, a so-called flank position of the branch. At the crotch positions at 90 degrees from that crack, going either way, and the other flank position underneath, there was no creep damage at all. So no cracks and no creep damage detected by replicas. So that tells me there's a large system load acting on that, as well as being a shortfall in the design and the fact they've used grade 91. Next slide, please, Pete. So this is the same branch after we've taken that particular branch out of service. We weren't able, because this was creep and the branch was so thin, it was about 10 millimeters in wall thickness, we weren't able to carry out a weld repair. If we do a weld repair with this, we have to remove all the heat affected zone. So that would have opened out the excavation too wide, given the thickness. So in this particular case, we had to rip out that T and put a new branch in place. But I think Pete's used this slide already, actually, but it shows the positions of the replicas. There's two on the top of the branch there, but you can also see on the far left a replica was carried out on the one of the butt welds as a part of the routine condition monitoring on that system. Okay, next slide, please, Pete. That's the result of the replica. So this is a times 500 magnification shot, acetate replica at the crack tip. So you can see the micro crack there, but also to either side of the micro crack, you can see the little black dots in the martensitic microstructure. So those are creep cavities forming on the grain boundaries of the structure. Okay, next slide. So this is the final example that we've got. This is another recent case that we looked at where we were doing replicas on a once-through cooler branch weld. So a once-through cooler is a means of collecting or cooling air from a gas turbine compressor, cooling it before it's reused to cool the gas turbine blades. But in doing so, what we do is heat up water, convert it into superheated steam. So this is one of the branches taking the feed water into this heat exchanger. So we've moved from a carbon steel material on the branch using an Incalloy 800 transition piece. We welded that using Inconel weld to a Type 321 stainless steel shell. So there's quite a few different materials involved in this transition weld. And you can see there that the etch that was carried out using Marble's reagent has formed this very dark line on the microstructure. So that dark line is on the heat affected zone, the fusion boundary between the Inconel weld and the Type 321 stainless. Now, if we look at the next slide, Pete, we can see a times 200 replica of what was seen across that fusion boundary. So on the far left, we've got an etched weld structure. On the far right, we've got the etched 321 parent shell material. And next to the weld, we've got this region that's not been etched, a very dark region that's been etched next to that. And then on the next slide, Pete, in more detail at times 500, you can see that darkly etched region has actually got a substructure to it. So it looks like there's carbides in there, possibly. You can see the twins on the far right hand side. So there is a substructure to that. But this does illustrate what Pete was saying earlier, in that there is a limitation to replicas. Next slide, please, Pete, which is the same photograph. The possibilities here are really that we've got an etch effect because of the dissimilar materials causing this light etch, this dark etch, or we could have a region of carbon migration. But even using the PMI techniques, the X-ray fluorescence detectors that we can take to site, we're not able to investigate the carbon content across that heat affected zone. So really the only way to solve this issue is to have a real sample of material back in something like a scanning electron microscope. So yeah, we're able to say something about what's going on with the microstructures and what we're seeing on that etch structure, but the replicas and the PMI technique didn't give us everything we needed for this investigation. And I think that's the last slide. So thanks for that, and I guess questions next.
Thank you, Peter. Thank you, Simon, for a very wonderful and quite interesting presentation. To be honest, this is my first time of coming across replication and examination techniques, so I'm a neophyte in this area. We do have about 11 questions tonight, and I guess that just goes to show the amount of interest that your presentation has engendered. So I'll take them in sequence. Our first question tonight is from Steve Tate, and the question is, and I read, I have not seen such a presentation before. Very interesting. Thank you. I was wondering who first discovered or invented this replication process.
Me and Peter discussed this, I think, recently. And I don't know the answer to who it was, but it must have been discovered by accident. It's a sort of probably someone playing with acetone and acetate strips and having the acetate strips stick to the fingers would be my guess. Pete, do you know?
Yeah, I don't know a proper answer to that, but most things are found by mistake, aren't they? So you could imagine that would be the case. Yeah,
but I do still find it amazing that we can get down to these micron scale resolution, looking at carbides and creep cavities and other features. It is amazing, really, the detail you can capture on a bit of acetate.
I guess so much of an eureka moment then, I guess. Our second question for tonight is from an anonymous attendee, and the question is, do you see this technique can be developed by employing artificial intelligence, AI?
So I think there have been attempts to automate, particularly the assessment of creep damage. Unsuccessful so far, but I would imagine, to be honest, that with AI you could teach it what a creep cavity looks like, and you could probably get quite a good assessment. I think that the difficulty would be that you'd have to have a fully automated microscope. So we typically take a microscope with us to site. So although we're not assessing the pipework directly, we're on site, and we would typically assess replicas that were taken the day before, and so we keep a constant update to the site. We use a manual microscope with a manual stage, so we would scan an entire replica. So a replica is about 25 millimeters by about 75 millimeters in size. We would do that 50 times magnification, and then we would do that a smaller area at 500 times. So if you had an automated microscope stage and an AI software, then I'm sure you could teach it to do that. I think the difficulties would probably come in the artifacts that you can get in replicas. So as I said, sometimes on sites it can be very difficult for cleanliness, and you can get some really lovely replicas where there's almost no imperfections, and then you can get other replicas where there are artifacts where you'd either possibly have to reject the replica and say you need a new, another attempt at it, and understand what the problems were and try and mitigate those for the next attempt. There can also be times where some artifacts could potentially look like not necessarily just creep damage, but it could look like other defects in the material. So that would be the real challenge, to try and teach the AI the difference between artifacts and real problems, and also to know when to not know and to have to ask for another replica to be taken because of uncertainty. But in theory, I expect, yeah, it can be done eventually.
It's worth saying there's a when you're looking at creep cavities under the microscope, you use a fine focus to go in and out of focus very at a small level, and the creep cavities twinkle at you. The best way to describe it. So you would need to integrate the sort of recognition of what you're looking at with some sort of link to the microscope to alter focus. I'm sure it can be done.
Well, as long as we still have the human brain, our jobs are still safe for now. Right. Our next question is from Ravi Shankar Siriki. And his question is, can you please provide the ASTM reference standard, replica silicon rubber method for in situ metallography?
In all honesty, I'd have to look that up. I don't know if off the top of my head. So I don't know if that's something we could get back to you with that you could then share.
That's fine. Also, your email addresses are both on screen, so I guess Ravi can always send you a mail directly to inquire and possibly initiate further discussions.
Yeah, sure.
All right, thank you so much. So our next question is from Billy Morrison, and his question is, I have used the acetate replication on refineries, mainly for creep. Is this your main use? And the second part of the question is, for the putty, would you use it for measuring, recording pit depths? What percentage of your work would be upstream, as in upstream oil and gas?
So I suppose the quick answer to the first question is yes, creep damage is our primary focus for this. And secondly, the putty, yes, you could use it to replicate pit depths. You'd have to make sure you did squeeze it, fully into the pit, and then you'd obviously have that permanent record of the pit depth. You could perhaps do more accurate measurements by some sort of CMM, something like that, remotely. Sorry, the last part of that question.
What percentage of your work would be upstream, as in upstream oil and gas?
Okay. I think in terms of replication, we tend to be on the downstream side. I'm not sure. I would imagine we could do upstream. I don't think there would be particular reason not to. I don't know about you, Simon.
No, replication, not so much. I think on the NDT side of it, yes, we've applied it across the industry, really, haven't we? And I think going back to the question of pit depth, I think there are other techniques that might be quite attractive. There are laser techniques that can map pitting and measure pit depths over sort of wide areas, lots of tubes. It's something that we are offering and other people do offer. So I think the sort of laser techniques for mapping pitting is a way forward.
All right. Thank you, Simon. Our next question is from another anonymous attendee, and the question is, how do we assess corrosion while in surface preparation the evidence of corrosion is mostly removed?
Yeah, that is a challenge. So obviously, if you've got pitting, so our typical process for surface preparation would start with grinding. So you would take a lot of the surface off. So if we're looking for creep damage, we would grind the surface and then we would gradually work down in grits till we get to a 1 micron finish. So yes, you would be taking off any oxide layer, removing any sort of decarburized layer as well. If you had surface corrosion and that was the particular interest in that instance, then you could either do no preparation and possibly do like a putty, or try the acetate method. Probably wouldn't be so useful for that because the acetate will rip on the undulations of the corrosion product. So you could use the putty. Another option would be to do a minimal prep. So you might be able to just do a very light grit, sort of 60 grit finish to remove sort of the general corrosion. But if you've got pitting, then that would show up and then you would be able to put your putty in and get the pitting. But with corrosion, it can be challenging.
Thank you, Peter. So our next question is from Alireza Salehi, and his question is, are all of the microstructural photographs shown prepared by replication? That's it within the presentation you've just delivered.
Not all of them, but there's no reason that they couldn't have been. The only reason a couple of them weren't was because I tend to do a lot of work on failure analysis and destructive testing, where I'm looking in cross section. So I took a couple of images. So the aluminium that I looked at, those were actually from the metal surface, but in theory, and there's no reason why you wouldn't get exactly the same appearance from a replica if I just took that section that I'd polished and etched and put a replica across it, it would have been exactly the same. So yeah, to be clear, they're not all from replicas, but they are exactly what you would see from a replica.
Thank you, Peter. Our next question is from another anonymous attendee, and the question goes, can we detect early deterioration of material by HTHA?
Yeah, I can answer this one. So I've been involved in this in a number of fertilizer plants in the Middle East. So we were using advanced NDT as a tool, but supplementing advanced NDT with replication, surface replication. This was always carried out on the inside of the vessels. Yes, on one occasion we were able to detect HTHA with that damage. Very similar sort of scale to creep damage, actually. Little micro fissures within the structure. So yes, it's been done.
If I may ask, what exactly is HTHA?
It's high temperature hydrogen attack. So you get under high temperature with hydrogen, you've got the hydrogen forms with the carbon in the steel and produces methane, which then is not mobile within the structure and sort of cracks open the microstructure to form little fissures.
Fissures within the material. Thank you.
Yeah.
Our next question is another one from Alireza Salehi, and his question is this possible to etch the replica? Is it possible to etch the replica? Would you please briefly explain how to make samples ready to watch them under the microscope?
Okay, so we actually etch the metal surface. So the etchant would depend on the steel or stainless steel or other metal in question. So once you've etched the surface, then we would partially melt the acetate onto that surface. And then once that's hardened and we've applied a black paint, we would then stick that to a microscope, a glass slide, for assessment under an optical microscope. So we're not actually etching the acetate. The acetate is being melted onto the metal surface to take up the etched surface.
All right, thank you, Peter.
Okay.
Another question from an anonymous attendee. Why do we not take replicas on the intrados of beds?
Yeah, sometimes we do, but what we found across the industry, and this is based on lots of sectioning of removed bends, was that, and this occurred after that bend failure that I showed you in 2006. A lot of work was done to understand the development of damage, and we found that the extrados was always a precursor to the, as long as the thickness was okay. You tend to get a thinning on the extrados itself compared with the intrados as far as the bend forming process. But if the UT shows that the intrados is thin, then that would trigger us to also look at the intrados with replicas as well. So it sometimes happens, but it's a ranking exercise. We use the information from the ultrasonic testing to decide whether we would need to.
Okay, so that definitely implies that the replication is a complementary technique and not standalone.
It's definitely not standalone, no. That early stages of that main steam bend crack, the damage was actually peaking mid-wall, and there wouldn't have been any detection of creep damage on the outside.
Right.
So ultrasonics are required for belts and braces to make sure you get a full picture of the component.
All right. Thank you, Simon. Our next question is another one from Steve Tate, and the question is, what is the temperature limit for safely taking replicas?
Okay. Yeah, so we do sometimes have people who turn their plant off and think we're just going to turn up and replicate. we don't have exact numbers. I'd say I've always been told if you can touch the pipework comfortably, then you should be able to get a replica. Obviously, we are putting acetate on there, so it will melt if you put it on too hot. And the other problem is when you come to peel it off, if the pipework's hot, the acetate is never quite as it doesn't harden quite fully, so you can rip it, tear it as you peel it off. So that's one of the main problems. I suppose the other problem is we are putting etchants on, which can then sort of cause fumes if you've got very hot pipework. But generally, I think that the limit is, as a rule of thumb, if you can touch it, then it's okay.
Yeah, the replicas we did in Saudi Arabia a few years ago, the ambient temperature there was about 42 degrees C. And that gives you a problem with the acetone as well. The acetone just evaporates too quickly, so it becomes difficult to apply the replica. So similar sort of temperature range, but yeah, once you're above 40 degrees C, it becomes quite difficult.
Quite difficult.
And also the other problem is low temperatures. So sometimes up in Scotland we've been replicating in the winter, and just getting the acetone to dry in those cold conditions can be very, very difficult. So you need a heat gun or something to then try and dry them. So cold weather can also be a problem, as can moisture. That can give quite problems with artifacts as well. So ideally, sort of general nice summertime weather is ideal. Dry weather.
Interesting.
Take
Thank you
heat
so
as well.
much. Okay, fair enough. Right, we have a question from Dr. Douglas Mills, and his question is, after the replication process, is the remaining surface more active than it was before it was cleaned? And if so, how do you cope with it?
Sorry, is the surface more active, did you say?
Yes, I'll take the question again. After the replication process, is the remaining surface more active than it was before it was cleaned? And if so, how do you cope with it?
Okay, I'd say it's not. So we would clean any etchants off with acetone, so they will be neutralized away. Because we're reaching a 1 micron finish, I generally feel that a higher polish is better in terms of corrosion resistance. Yeah, I don't think we've ever had a problem, but it might be material specific. If you had a particular material that there could be an issue at some point, but we'd have to assess that if we had an unusual material.
All right, thank you very much. So we have a couple of comments. One again from Dr. Douglas Mills saying, thank you very much for a very interesting talk. And a question from Elizabeth Hickson. And the question is, what is a typical procedure for dealing with the etchant on site? For example, stopping it affecting the equipment below the testing location.
Do you want me to answer that?
Yeah, if you like.
Yeah, I mean, we have to be very careful. We have the risk assessment method statements that we produce for going on site to address these issues. We have to think about not only the equipment, but people that might be working below. And we take all precautions to make sure that we don't drip acetone and etchants onto equipment. But they can be quite destructive. They can be quite destructive to the equipment we use to replicate. I've seen polishing wheels and polishing bits of kit melted with acetone, and so we'd have to be very careful. The operator, the technician that does the replicas, will be wearing a dust mask during the gritting stages, so we don't breathe in dust, metallic dust, and also wearing things like nitrile gloves. So a lot of PPE considerations as well. So yeah, we are very, very aware that the chemicals we're using can be quite damaging, and we take every precaution. We lay down sheets, and we make sure people are not working below us, and all those sorts of precautions. And then cleaning away the debris, and we use a lot of cotton wool swabs for the acids and the acetone. So we take all that away with us from site in chemical bags for proper disposal afterwards.
All right, thank you. So our next is a question and a comment, and it goes, thanks for an excellent presentation. Have you ever been called on to perform replication on flare tip materials such as 310 stainless steel or 800H? Thermal damage such as intermetallic formation from mal-operation of this type of equipment is often a concern. So effectively, have you done replication on flare tips?
On what, sorry?
Flare tips.
No, I don't believe we have. But in terms of those materials, I think the Incloy 800 is what Simon was showing in the last images. And 310 stainless, we would also be able to replicate etch that. So in theory we could, but we haven't done those specific components.
No? All right, I guess that's a potential opportunity then. For sure, for sure. Thank you. So the next question, and we're almost done for the day, is what is the most common analytical tool for interpretation of the replica?
I'd say the optical microscope. As I say, because we aim at creep damage, we're taking a curved surface of a pipe or undulations over a weld and flattening that out on a glass slide for optical microscopy.
Okay. And the last question I will answer, and the question is, can attendees get a copy of today's presentation? And the answer is yes. It will be available on the Aberdeen ICorr website in the next few days. So thank you so much. Oh, there is another comment here. I apologize, from Selva Kumar Arunachalam. And comment is, thank you for a very wonderful presentation. It was really interesting and useful.
Okay, thank you.
Glad to hear it.
Thank you, Peter. Thank you, Simon. We really enjoyed your presentation tonight. I guess the attendees really engaged with it as well, as you can tell from the number of questions that have been asked. So we'll like to give Peter and Simon a virtual round of applause as we draw tonight's session to a close. Thank you so much. The recording will be available on the YouTube channel in the next couple of days, as will the presentation. So with that, I will say good night, everyone, and thank you for attending. Goodbye.
Thank you.
Thank you.